Hello and welcome back to the Deep Dive. Today we are jumping straight into Class 12 chemistry, specifically Unit 6, halalkanes and halurines. And I have to be honest, I was sitting with the notes this morning and I just hit a bit of a logical wall.
A logical wall, that's usually a good sign. It means you're actually thinking about it, not just, memorizing. What was the problem?
Okay, so it feels like a total contradiction.
Right.
We're talking about nucleophilic substitution, right? That's the main reaction in this whole
The
chapter.
bread and butter of Unit 6, yes.
Right. So here's my logic. Nucleophiles are electron-rich. They're negative, or at least they have a lot of electrons.
Correct.
And halogens, chlorine, bromine, iodine, they are also super electron-rich. They're electron-negative. So if I am a negative nucleophile and I see a haloalkane with this big negative halogen sticking out, shouldn't I just run away?
Because, charges repel.
Exactly. It just feels like trying to push two magnets together,
Yeah.
the wrong way. Why on earth would a nucleophile attack a haloalkane instead of being repelled by it?
That is, without a doubt, the single most important question you can ask in this entire unit. If you get that, you get organic chemistry. If you don't, you're just learning reactions by heart.
So what's the answer? Why doesn't it just bounce off?
The answer is in the topic for today, the nature of the CX bond.
The carbon-halogen bond itself.
Yes, that one bond is mission critical. It's the engine for the whole unit. I mean, think about a simple alkane like ethane. It's boring, isn't it? It doesn't react with much.
You just burn it, basically. That's it.
Exactly. But you swap out one hydrogen for a halogen, and suddenly the whole molecule it wakes up, it becomes reactive.
This bond is the only reason any of this chemistry even happens.
It is the only reason. And for everyone listening, if you're worried about your exams, understanding this bond, it's the foundation for predicting almost every question on nucleophilic attack. So let's solve your magnet problem.
Please do.
Yeah.
Because right now, all I see are two negative things crashing into each other.
Okay, let's go to the simplest possible level. The textbook calls the CX bond a polar covalent bond. But those are just words, aren't they? We need a picture.
Right. What's actually happening to the electrons? We've got a carbon bonded to a halogen. They're sharing electrons. That's a covalent bond.
Well, theoretically they're sharing, but in reality, it's not a fair partnership at all. You have to remember where the halogens are on the periodic table, group 17.
Right next to the noble gases. They're desperate for one more electron.
Exactly. So they are incredibly greedy for electrons. We call that property electronegativity. I want you to imagine the halogen is like a magnetic vacuum cleaner.
Magnetic vacuum cleaner. Okay, I like that.
And it's attached to the carbon. So even though they're supposed to be sharing those electrons, the halogen is just pulling all of that electron density violently towards itself.
So the electrons aren't sitting nicely in the middle between the two atoms.
Not even close. They'd be swarming around the halogen. The halogen is monopolizing the whole cloud.
So the halogen gets, stuffed with electrons?
Correct. It becomes electron-rich. And in chemistry, we say it gets a partial negative charge. We write that as delta minus.
Okay, but see, that brings me right back to my problem.
Yeah.
The halogen is delta minus. The nucleophile is negative. Repulsion.
But you're looking at the wrong end of the molecule. Forget the halogen for a second. What about the carbon?
The carbon.
If the halogen has stolen the blanket, what happens to the poor person on the other side of the bed?
They're left freezing, uncovered.
Exactly. The carbon is starved of electrons. It has lost its fair share of that electron cloud. So, while the halogen becomes partially negative, the carbon becomes electron poor. It gets a partial positive charge, delta plus.
Oh. Okay. I think I see where this is going now.
The nucleophile is not stupid. It doesn't go for the halogen. It sees that negative charge and thinks, nope, I'm staying away from there. But then it spots the carbon.
And the carbon is positive.
And nucleophiles love a positive charge, so it's like a rescue mission. It completely bypasses the negative halogen and attacks the starving carbon directly.
That solves the puzzle completely. It's not attacking the negative part, it's attacking the positive part that the negative part created.
Spot on. That separation of charge is everything.
Okay, so for the students listening who need to write this down for an exam, what's the proper definition?
All right, here is the anchor definition you need. If you're asked, you write. The CX bond is a polar covalent bond in which the halogen, being more electronegative than carbon, withdraws electron density.
Okay, withdraws electron density. Got it.
This creates a partial positive charge on the carbon, making it susceptible to nucleophilic attack.
Susceptible to nucleophilic attack. That is the key phrase, isn't it?
It is, and I have to mention a huge mistake we see on exam papers every single year. Students draw the reaction arrow, the curly arrow, pointing to the halogen.
I can see why, though. The halogen is the interesting atom. It's the halo in haloalkane.
It is, but it's chemically wrong. If you point that arrow at the halogen, you're saying a negative thing attacks another negative thing. The examiner will just strike it out immediately. You have to aim for the carbon.
Attack the carbon, not the halogen.
Right.
Right, I want to lock this in with another analogy. The vacuum cleaner is good, but is there something more physical?
I like the tug-of-war analogy. It really captures that tension in the bond.
Okay, walk me through it.
Imagine carbon and the halogen are in a tug-of-war. The rope is the bond, the electron pair.
Okay.
Now, the halogen is like a professional weightlifter, and carbon is, well, carbon's just an average person. The halogen is just steadily pulling that rope over to his side. Carbon is still holding on, but he's lost his balance. He's leaning forward, weakened.
And that weakness, that exposure, that's the partial positive charge.
Yes, and nature doesn't like that imbalance. That weakness on the carbon sends out a signal to the whole solution saying, I need electrons. And that's why the reaction happens.
It's amazing because without this idea of polarity, organic chemistry just, it wouldn't work, would it?
It would be totally different. And historically, this was a massive breakthrough. Back in the 1920s, 30s, chemists like Ingold and Hughes were trying to figure out how these reactions work. They couldn't see the atoms.
They were basically working in the dark.
Pretty much. But they figured out this polarity must exist. They realized that without it, you can't explain why halides are such good leaving groups.
Ah, leaving groups. Another one of those key terms.
Well, think about the end of the tug-of-war. When the bond finally breaks, who gets to keep the rope?
The weightlifter. The halogen.
Right. The halogen takes the electrons, the rope, and leaves. It leaves as a stable negative ion like bromide or chloride. And because it was already pulling the electrons, it's actually happy to take them and go.
So the polarity sets up both the attack of the nucleophile and the easy departure of the halogen.
It orchestrates the entire reaction.
Okay, I want to try a mental movie for everyone listening. I think visualizing this is the only way to remember it under exam pressure.
Good idea.
All right, everyone, if you can, just close your eyes for a moment. Picture two balls in space.
Right.
One is carbon, one is bromine, and there's a rope connecting them.
The bond.
Now, look at the aura around them, the electron cloud. Around the bromine, the cloud is thick, it's dark, it's dense, it looks heavy.
That's your delta minus.
Now, shift your focus to the carbon. The cloud there is thin, it's pale and wispy. It looks, well, hungry.
That's the target.
Now, in comes the hero, a bright blue dot, the nucleophile. Zipping around, it sees the dark cloud of the bromine and just bounces off.
Yeah.
Repulsion.
Exactly.
But then it sees that pale, hungry carbon. It zooms right past the bromine and smack! It hits the carbon. The rope snaps, the bromine flies away with the electrons, and the nucleophile now sticks to the carbon.
That is the SN2 mechanism in a nutshell. If you can see that movie, you can answer the questions.
Speaking of real life, does this actually look like anything in the lab? Or is all just theory?
Oh, it is very real. Take a classic school lab experiment, reacting 1-bromobutane with aqueous potassium hydroxide, KOH.
Okay, 1-bromobutane.
Right.
That's liquid, right?
Yes, an organic liquid.
Yeah.
So you mix it with the aqueous KOH, maybe heat it up a bit, and a reaction kicks off.
And the nucleophile there is?
The OH minus ion from the KOH.
So following our movie, the OH minus hunts down the carbon that's attached to the bromine.
Precisely. It attacks that carbon because it's positive. It kicks out the bromine, and poof, you don't have a haloalkane anymore. You've made butane 1-ol. You've turned one functional group into another.
And that whole transformation depends 100% on that initial bond polarity.
100%. In fact, this is the secret weapon of the entire pharmaceutical industry.
Drug design. Seriously.
Absolutely. Imagine you're building a complicated drug molecule, like a new antiretroviral. You have this huge carbon skeleton, and you need to attach one specific functional group at one specific spot.
Like trying to snap a Lego piece onto one particular stud.
Exactly. But carbon chains, well, they're boring. There's nowhere for the Lego piece to snap on. So what do chemists do? They first attach a halogen to that spot.
So they install a target.
They install a target. By putting a halogen there, they make that one specific carbon atom hungry and positive. Now they can throw in their real Lego piece, the nucleophile, and it will attack exactly where they want it to.
So a halogen is like a laser pointer for a chemical reaction. Attack here.
That's a great way to put it. It effectively marks the site for modification. Without that polarity, Building complex medicines would be incredibly difficult.
That's amazing. It really takes it from just lines in a textbook to how we actually engineer things.
It's engineering at the molecular level.
Okay, this is all making sense.
Yeah.
But now I want to shift to the exam safety zone.
The clarity checks.
Yes, we've gone through the source material and found these specific lines that always trip students up. I'm going to read them out, and you can explain why they're so important.
Let's do it.
Clarity line number 1. In the CX bond, electron density is pulled toward the halogen.
This is basic, but it's vital. It decides your delta plus and delta minus. If you get those signs backward on a diagram, you're telling the examiner you've misunderstood the entire concept. It's a huge red flag.
Okay, clarity line number 2. Halogens are good leaving groups because they can stabilize the negative charge.
This explains the end of the reaction. We touched on it. If the halogen wasn't happy to leave with the electrons and be a stable negative ion, the reaction would just get stuck.
Right. Now for the tricky one. This is where I got confused. Clarity line 3. Bond strength decreases down the group. CF is strongest, CI is weakest.
This is just about size. Fluorine is tiny, so the bond is short and strong. It holds on tight. Iodine is a huge atom, so the bond is long and stretched out. It's a weak bond.
Okay, that makes physical sense.
Oh.
But here comes the trap. Clarity line 4. A more polar bond does not automatically mean more reactive.
Yes. The big one, the polarity versus reactivity paradox. This is a classic multiple choice question designed to catch you out.
Okay, let's break this down. Fluorine is the most electronegative element.
It is.
So the CF bond is the most polar bond possible in this series. That carbon must be the hungriest of all.
That is absolutely true. It has the largest partial positive charge.
So logically, it should be the most reactive. It should be screaming for a nucleophile.
The invitation is there, yes.
Yeah.
The attraction is very strong. The nucleophile wants to attack. But remember our tug of war.
Yeah.
For the reaction to happen, the rope has to break. The nucleophile has to be strong enough to snap that bond.
Yeah.
And the CF bond is like a steel cable. It's incredibly strong. It doesn't matter how much the nucleophile wants to attack. It just can't break that bond.
So it's all invitation and no follow-through.
Pretty much, yes.
Yes.
High polarity, but extremely low reactivity because the bond is just too strong to break.
Now let's look at the other end, CI.
Iodine is barely more electronegative than carbon. The polarity is quite low. The invitation is weak.
But the reaction is fast.
Very fast. Because the CI bond is so long and weak, it's like a piece of old string, that the moment a nucleophile even gently nudges it, snap, it breaks.
So bond strength is more important than polarity for reactivity.
In this context, bond strength wins the argument. Always.
Listeners, put a big star next to this in your notes. If the exam asks which is more reactive, don't look for the most polar bond. Look for the weakest bond, iodine.
Correct. The reactivity order is IBRCLF, the complete opposite of the polarity order.
That is such a classic exam trap.
Don't fall for it.
Okay, one final clarity line.
Okay.
The CX bond remains polar, whether the halocane is primary, secondary, or tertiary.
This is just a reminder that this fundamental principle doesn't change. Even in a big, crowded tertiary halocane, that carbon attached to the halogen is still positive. The mechanism might change. You might go from SN2 to SN1, but the reason the reaction happens is still that polar bond.
It's the universal truth of this unit.
It is.
This has been brilliant. I feel like I finally get why my magnets don't just repel. Let's do a really quick summary for revision notes.
Sure. 4 key points.
Point 1, core idea.
The CX bond is polar. The halogen pulls electrons, making the carbon positive, or delta plus.
Point 2, the mental image.
Remember the target. The nucleophile ignores the negative halogen and attacks the positive carbon.
Point 3, the application.
This polarity is why we can make alcohols, amines, and even complex medicines. It creates a reactive spot on an otherwise boring molecule.
And point 4, the big trap.
Reactivity is decided by bond strength, not polarity. Iodoalkanes are the most reactive because the CI bond is the weakest.
I think the takeaway is polarity sends the invitation.
But bond strength decides if the party actually happens.
I love that. Well, thank you so much for breaking this down. It makes the next topics, SN1 and SN2, seem a lot less intimidating.
That's the whole idea. Once you understand the why, the how becomes so much easier.
Exactly. Keep that magnetic vacuum image in your head, everyone. It'll really help. Until next time, happy studying.
Good luck with your revision.